All right, so in this example, we are going to look at how we can apply our understanding of a definite integral into finding the work done by lifting a rope. Okay, yes, it sounds simple, but lifting a rope, surprisingly, is more challenging than we think. But it's not that heavily challenging to the point that I mean, it's not that heavily challenging so that we can now put that into our study for the Calculus 2 students here. Okay, so let me now, before I actually get into the actual worded description right here, let me just describe the problem here, kind of like in the situation. Okay, and then from there we're gonna start heading into the actual wording of the problem right here. But it's just like, think about a lot of time when you go to a harbor that you see those kind of ropes where they use to tie a boat or a ship to the nail right there. Okay, and so those are the heavy ropes. I'm talking about a really heavy rope, or like a cable chain. That's the same idea right there. Okay, we're talking about very heavy ropes. And the number one characteristic, we know that, let's assume that the rope here is uniformly having a uniformly distributed weight. So the idea now is just think about on the ground. You're on the ground and you have ropes, and then being being coiling on the ground right here. Okay, and now think about it, the rope is a cable chain, for example, with steel or metal, then it's pretty heavy. Okay, so now if we want to lift that up, from the ground, and then from that kind of problem, there could be another problem where there could be another situation where the rope is kind of dangling on a wall right here. So this, you can think about, here's a cable chain right here, and it's hanging dangling on along a wall right here, a tall wall right there. Okay, but so the idea now is that if we lift the whole thing, so either we lift it off from the ground to a certain height, if we want to reach that to a certain height, or just that, and we try to, wherever that hanging cable is, we try to lift it so that all of that is going to be lifted to the top. Okay, we want to try to lift that to the top of the building. So two situations. It looks at first different, but in the end, these are similar situations right here. We're lifting the cable, we're lifting the rope. So here's what I'm trying to explain right here. If we are, now imagine if the rope is completely on the ground as a whole pile of rope right here. I mean, one rope, but it's coiled, so we have what we have in front of us is a whole pile of rope. Because I'm asking you to imagine that about those heavy ropes that you see at the port, where people tie a boat or a ship to the nails like that. Okay, so those cables, if we for any reason take the whole pack, lift it up, okay, then that means it's just the weight. It's just the weight here, and this is the amount of force right there. Okay, because now with your basic physics understanding, then any rope here, I'm talking about now heavy ropes, means it has a certain mass. So with that mass right here, we multiply, so mass times with acceleration, and then we multiply that with the height distance. That gives us the total amount of work. Weight times, or force times the distance. That's the concept of work, again, that I mentioned that in the general discussion lecture. And so, and again, the situation here is that if we can possibly pack the whole, or take the whole pack, lift it up, or just like that, think about, there's a man standing at the top of the building here and trying to take the whole, somehow grab the whole, and lift it up to the top of the roof. Then that's making it simple story. Okay, that's making it simple story. So it sounds simple, but on the other hand, it's not as simple like you think, because taking the whole package here and lift it up, it's going to be super heavy, usually heavier than any of us man being can get it done. Any one of us physically can get it done. Take the whole pack, lift it up, because I'm talking about heavy cable chains, okay, to the points that could be tons in weight. And so lifting that up, well, with the mass, and in standard physics right here, gravitational acceleration is a 9.8 meter per second square, right there, multiplied with the mass given, and then we're lifting that up with this height. This is for the distance to exert that amount of force going against gravity to lift that up. That takes a lot of effort. And like I said, usually those ropes are heavy, those cable chains are heavy, so that, you know, it's nearly impossible for one man to physically, and then we don't want to take too many men to lift it up, okay? And then if we're lifting it, then we're, in the end, we're a man, we're a human being, we have a certain limitation in height, so we can't lift it too far, okay? And so now I'm talking about this plan. Seems like it's work. It seems like it's the way we take the whole pack, we're lifting it up, okay? But it's going to be extremely hard right there. It seems simple at first, but it becomes extremely hard, especially if we're thinking about how do we make the man here, they're standing on top of that building, try to wrap the entire coil, wrap the entire cable into one pack and then lift it up from this bottom up. It's not a simple thing at all, okay? It's not a simple thing at all. So we gotta change plan. So that plan at first initially thought to be a simple plan, and now we have to change plan. So the idea now is that lifting, yes, lifting, the idea is just we're trying to lift it to a certain height as desired, but why don't we lift it by pulling it up one by one, step by step? I hope there's a cable in front of me here, but you know, the idea is there's a cable, heavy cable in front of me, okay, and we're lifting it. So, you know, if I need to lift it at this height right here, then I stand on that height and I lift it up, okay? And as the idea now is that as we lift part of it, as we keep lifting part of it up, then the part that already been lifted, after some amount that has been lifted, then the amount left over will keep getting lighter and lighter, making it easier to lift. And so the idea now is that, so plan A, if we lift the whole thing all at once, lift it up, then all that weight goes with us the whole path through, the whole distance. But now if we're doing gradually, lifting up one by one, pulling it up, as I said, one by one, then we're gonna keep having, well, it is at start, it's gonna be very heavy because all that weight of the cable remains there for us. But as we start lifting up some part of that, then it's keep reducing the amount of leftover cable. After we have pulled away some X amount of cable, after we already have lifted some X amount of cable, then the remaining amount of cable is keep getting less, and so become lighter and lighter for us to lift. So the amount of force keep decreasing, or basically the amount of force is changing, keep changing in you know, being lessened and lessened and lessened, okay? So that in that way right here, seems like plan B now is going to be the better one right there. And so as I pointing that out right here, we're going to approach that understanding. So the idea now is that it's nearly impossible to take the whole pack and lift it up. It's hard. So we come up with that idea that seems there's a hope, good hope, that as we lift, and after some amount being already lifted, things will keep getting better in the sense that it's getting lighter and lighter, less force being exerted as time goes on. Okay, and so that's the idea, that's the plan that we keep in mind right here. So the same with that, the man can stand up at that height right here and start lifting it up one by one. Okay, and then the man standing up here, he can grab that end of the cable. The man standing on top of the building, he can grab that end of the cable and start lifting it up. So this length is gonna keep getting less and less and less, keep getting reduced and reduced and reduced. And as we reduce the amount of length right here, the cable gets less weight. The remaining part of the cable that needs to be lifted, the remaining part that needs to be lifted, we get less weight. That's the idea right here, and it keeps getting easier and easier to pull it up. All right, so that's the fundamental, the generality of the plan here, and that's why now when it comes to the kind of force, the kind of work that we need to use force, but continuously changing. That's where we have to start applying the calculus right there, so that we can see how we can accumulate all of those changing amount of work. because at every instance we're gonna have to spend different amount of force, different amount of efforts with that. And so that's why, little amount of efforts accumulating up, we're gonna have the total amount of work, the total amount of efforts. Okay? And so now at this point, after so much mentioning about that, so at this, before we head into the actual problem, so now I have to mention again, we have to we definitely need to view this video lesson after seeing my general understanding about how we apply integral into doing a work problem. Okay, so this example is just simply one among the many examples out there where we can apply the definite integral into finding work. Okay, and one of the very famous and common problems in physics. Okay, and so now let's have a look over at our, so in this example I am going to have two little problems right here. So let's call this part A of our example. This is part A right here, the more basic version, the more fundamental version. Actually, I shouldn't say it basic, but the fundamental version. So now the wording of the problem says a 28 meter uniform, so these are two characteristics right here. It's 28 meters length, 28 meter long, being uniform, and that means it's the same weight at every point on the chain right here. So 28 meter uniform chain with a mass density of 2 kilograms per meter is dangling from the roof of a building. How much work is needed to pull the chain up onto the top of the building? Okay, so now reading this wording description of the problem more clearly, then it is that problem that I tried to describe in brief earlier. It's this problem right here. Think about this is the cable, that 28 meter long cable right here, and it's a uniform cable. So what does that mean by uniform cable? That means, see, it has whatever the thickness is, but the total weight of the chain here is divided. If we divide it into equal subsections, so imagine that this is your cable right here. This is your cable. Then if the cable here, once the cable is divided into, and doesn't matter how many subsections that cable is divided into, but as we divide the cable into the equal subsections like this, and every little section has equal weight, equal mass. That's what it means by being a uniform the weight cable, or just for short a uniform chain. And then this is actually a cable chain right here, a heavy kind. Okay, so think about construction workers. They work with these cables a lot. So here we're not at a harbor where the cables is for that purpose, to hold a ship to the harbor, but this is a cable, the kind of cable where we see at construction sites right there. So it's hanging, dangling on a wall right there, and we're trying to lift it up. Okay, so we have to give up that plan of taking it all one cable and lift it up. I mean, it seems like an easy, simple plan, but the work when we're doing it, it's not that simple, especially for any, for the human being. Okay, and so now let me really draw the picture here. So here's the tall building, and it does not matter how tall that building is. I mean, at least the building has to be, according to the wording description, then the cable itself is 28 meters long. Okay, and so in that way, being 28 meters, then it makes sense that the building has to be at least 28. If the building is only 28 meters, then the cable is going to reach from the ground and all the way up to the top. That's how long the cable is. Okay, 28 meters, but the building could be longer than that. So in either way, it's going to be having the same way to handle the problem. So here's our cable right there. Here's our cable. Okay, so just like I said, the plan now is that it's impossible for us to grab the entire cable, roll it up into one roll, wrap it up into one coil, and pick the whole pack. It's not possible. Okay, it's not physically possible for any human being right here. And so we're going to do that in a way that we're going to have a man standing here, and it only needs to take one man. Usually it works. The man right here standing there is going to start lifting up. Okay, we're going to start lifting up one by one. All right, and then so at every little instance where we start shifting even a small amount of lift, a small amount of cable being lifted, the remaining amount will definitely have less weight. Okay, have less weight. And so as we keep lifting, as more cable is being lifted to the top right here, the length remains to be lifted. Keep getting less and keep getting less and keep getting less. Okay, so in that way I'm explaining. I'm going to say, I'm going to let X and let the cable be hanging like that. Maximum length here, maximum length from the top of the building down to that is 28. And we want to go, yes, it's 28 meters because that's maximum length of the cable. And so, and now it's worth it to mention a little bit here, but if we're looking at the convention, the units convention here, we are working with the SI convention, the International Metric System for here for the SI units for force and weight and work. Okay, and so now in that way I am going to name my variable. But for this problem right here, I'm going to name the variable X right here is the amount. I mean, we don't usually have to do this because some problem it's easy to understand, but some problem it's not straightforward. So we have to clearly state our variable. Okay, so in case you have seen some other videos, the examples of mine regarding this kind of problem, I mean the kind of problem where we're doing work. Some other examples I might not need to define or state the variable clearly, but here I have to. So let X be the amount of lifted cable. Okay, or lifted change, or the length of the lifted. Actually, the amount of lifted chain. And what I mean is the amount that was already lifted and stay on top of the building. Okay, and so that means in that way we have 28 minus X will be the remaining, okay, the remaining length of the cable or of the chain. Okay, but this is to be lifted. This is what's happening always at any moment right here. So at any instance where you have already reached any X amount of chain being lifted, then we have 28 minus X being the remaining length to be lifted. That's the idea right here. Okay, and this is what determines how much weight that you need to exert at every instance that you have done. Okay, and so now you know that it's the remaining length. It's generally described as a 28 minus X, provided we know the meaning, the definition of what our X means. Okay, and so in that way right here, so now with this weight right here, now I'm going to swing back to the wording of the problem here and point out another thing. See, so the weight here, I mean this cable here is a uniform chain. It has a mass density of 2 kilograms per meter. This is another good good characteristic for us to understand right here. Because it's just whatever material, it could be steel, it could be the iron cables, but 2 kilograms per meter, or whatever that is, right? But now, when we have that many meters left, when we have that many meters remaining, after we have pulled away, after we have already pulled up to the top, some X amount of meters, some X meters being lifted to the top, then we have that remaining, as you already clear. So as we still having that much length left, then the weight here, I mean the actual mass, okay, I shouldn't rush into the weight yet. So the mass here, the mass of the remaining is going to be, or how about the mass to be, because what matters here is what's left to be lifted, okay, so the mass to be lifted will be, well, 28 minus X is the remaining length to be lifted, but we're going to multiply with 2 kilograms per meter of length. It's the way how the cable is. So 2 times 28 minus X. So at any instant where you have already pulled X meters away to the top of the building, then we always going to have 28 minus X length left, but then together with the mass density, it's 2 times with that length. Okay? And now, so that's mass. And then basic physics now is telling us that now mass is how much material. I mean, a lot of time we think of that as how heavy. I want to say that for the the physics sister, your physics instructor, to clearly distinguish between the mass and the weights right here. But mass is not exactly weights, okay? A lot of time in our daily language term, we use that a little loosely, and we're using that a little unclear, but mass is related with weight, but it's not exactly weight. Mass is just how much material in that object, of that object. Any one of us here has a mass, how much material that we're built of, okay? So the mass to be lifted is 2 kilograms times with that length here, because this is mass density, okay, and mass per unit, and then here we're multiplying that with the length. But now the weight consequently will be, according to Newton's law over here, the weight will be, because famously everybody knows that any living object or any object on this earth or any object exists in this universe. Specifically now we are landing on Earth right here, we're staying on Earth right here, then there's gravitational acceleration. Okay, so the weight now is simply just the mass being 2 times, generally expressed as 2 times 28 minus x, but we take that mass and we multiply with acceleration, because the weight is also a force that's pulling the object down like that. So it's 2 times, as a quantity, it's 2 times with that, but multiply with, on Earth right here, on this Earth, only on this Earth. If we're doing on Mars, if we're doing this math problem on Mars, it has to be a different number, but 9.8 meter per second squared, that's the units for acceleration. But acceleration multiplied with mass gives us a total weight. So again, I want to leave all that detailed understanding for your physics instructor to explain, but any living object, this eraser, this dry board eraser that I have right here, it has a mass, so gravitational force, gravitational acceleration together with that, creating a force that's holding it always on the ground. I stand on the ground instead of flying in the air, instead of flying in the air simply because there's weight. My body mass multiplied with the gravitational acceleration being on this Earth, 9.8. And that's how it becomes a weight, which is the force that keeps me standing and attach my feet on the floor, on the ground. Okay? And so just like that, now if we have a cable being at this total mass right here, generally 2 times 28 minus x, then we're going to take that general mass and multiply with the constant gravitational acceleration here being 9.8. So like I said earlier, if we're doing this math problem in Mars, maybe Mars has less or more the gravitational acceleration, and that number here will change if we go to a different world. But here in our world here, it's constantly 9.8. Okay, so we're multiplying that with this, and that gives us weight. So why does weight matter for us here? Because now if we want to lift that up, then that means we have to exert force to go against that amount of weight that's pulling it down. Because see, as I explained earlier, weight is keeping it down on the ground. So in order to lift it up, we have to need the amount of weight. We have to exert the amount of force at least big enough with this amount right here to pick it up from the ground, to make it depart from the ground, to make it leave the ground. Okay, so that's why weight is another way of thinking about force right here. Okay, so all of that is I just want to point out that weight is force. So now we have force, but see, you already start having a sense that the force amount here is not a constant amount, because it depends on how much we have pulled how much we have already pulled the chain away. So if it's x, it being the amount of chain that already be lifted away, then the weight here is going to keep getting less and getting less. It's a continuously changing the weight like that. Okay, so now. So that's the weight, or the force right here, the changing force right here. Allow me to swing on my other board because I'm running out of space here. But so now, or maybe let me one more time swing back to this and utilize that picture. So now, yes, the total length is 28. Allow me to use a different color ink right here. How about in red to represent the amount? So at any instant, let's say at some instance where you have already pulled, your remaining length here is 28 minus some x right here. Okay, so at any instance where you have already pulled away some x meters of length, of cable length right here, then of course you have 28 minus x being the remaining length. And so But in the end, at every instant, that amount is being moved. That weight we're exerting, this weight we're exerting right here is used to move the remaining length right here to a certain distance. And that certain distance here is the infinitesimally small change in this direction. So if I call the length here being x, then this is, yes, that's dx right there. So dx here, this amount of small arrow, that's dx. And that's how much, and the idea is every instant we change, we have a small change. Every instance that we lift, right, then the next instance we already made a little distance. And so ideally, if we can reach to the infinitesimally small change in distance, so that dx right here will be our distance. All right, so in that way, dx is our distance. So if we can reach all of that, the distance, the idea now is the more precise we have, the more infinitesimally small that we can make our distance here, the more precise the total accumulation is going to get. Okay, so now on my other board, allow me to formulate the whole idea right now. Okay, so now I'm going to call that dx is really the distance or vertical distance. All right, it's the vertical distance to left. Okay, and again, it's a distance. That's the key idea. That's vertical distance to left. Okay, but the idea is we want the dx, that distance is to be as small as possible, to the point of being infinitesimally small. Okay, but so now we got distance. We know how much force we need to exert on our remaining length of the cable right here. And so now, with a small, so as we exert force to move our remaining length of the cable an infinitesimally small distance vertically up, then now we can multiply force, 2 times 28 minus x times 9.8, this is force, multiply with dx right here. Now this is why I was saying earlier, we need to view this lesson after we have viewed my general discussion video lecture about how to apply as a generality, how to apply the integral, a definite integral into doing work problem. The problem to find how much work we spent, because here, this is what I brought in the general lecture, what's so-called the little amount of work. This is the little amount of work here, the work to lift the remaining length, any remaining length at any instance, some infinitesimally small distance. Okay, so this is work, and yes, this is the amount of little work that I call it's a dw. So I also introduced this dw back in my the general discussion lecture. Okay, and so now the idea again, so the only fundamental now we stay with, and that's why again it is important to view that general discussion lecture before we get into this, so that I introduced there is quite a few details being the general details, and here in any of these examples, it's the kind of details that apply to any of those different situations, different various situations. So now we're accumulating all of the little work amount from its start to the end. That's going to be giving us our total work. Okay, and I have introduced all this in our understanding, in our general discussion lecture right here. Okay, so this is the little work amount, all of the little work amounts again. And so accumulating all of those little work amounts, that will get us into the total amount of work. And so now it's just a matter of producing the integral. An integral is accumulation. So now we're accumulating from some start, and we will find out how much the start is and how much the end is. Okay, but so the work amount here is that expression 2 times, the little work amount is 2 times 28 minus x times 9.8 and times a dx. Times a dx. Okay, and so now let's check for consistency. Let's check for some consistency. So when I started introducing to my students or to anyone viewing this lesson about the idea of an integral. And even before that, when we start getting into using antiderivative or indefinite integrals, then I always say, and I want to always keep any of my problem to be consistent with what I've taught earlier. In our expression here, we have a d expression already. We already had a d expression, and that d expression now is determined that to check for consistent, then the entire expression on the function has to be in terms of x to be consistent with this d expression, where it indicates that the main variable is the x variable, and everything else is constants. Okay, either constant coefficients or constant term like that. Okay, and so now in that way, let's look for the start and the end right here. Now, looking for the start and the end of the accumulation is not really direct from the picture here, because the picture is only describing the situation. But you have to think about it. We start accumulating when the chain was completely, we start the accumulation before we pulled anything up. When x equals 0, that means when the chain was all the way down here. But that could be a little bit misleading. When in my years teaching, when it gets to this problem, a lot of time I keep having students mistakenly think that the beginning is 28, and then we pull it into its 0. But actually, you look at my x right here. X is the amount of lifted chain, and so it makes sense that we start lifting. So the beginning of our accumulation work begins when we start out with zero amount of chain being lifted. Okay, and then at our ending point is when we finish completely. That means when x is 28, because the x variable here. That's why in this problem it's a little hard to see that in the problem, because when people are looking at the picture, they might see it's from bottom up, but bottom is 28 meters away from the top of the building. So they think that this is it goes from the 28 down to 0. But the idea now is once we define the variable being x right here, okay, then the accumulation happens when we first started out at that very initial moment. Then we got 0 amount of chain being lifted. So x equals 0 at start. X equals 0 at start. That's how we understand it. Consequently, right out from this definition. And then x will equals, once we're done, completely done, the x equal 28 at the finished or at the end. That's how. Okay, and so now we can take that and bring that into our integral setup right here. So with this integral setup, we now have a complete integral. To find the total amount of work, it's accumulation from 0 to 28. Okay, from 0 to 28. Okay, we're accumulating from when we started out having 0 meter pulled up to the top, and then we're accumulating that until we reach to completely 28 meters, completely be on the top of the roof right there. Okay, on the rooftop right here. So again, so now this is a complete integral, but before I proceed into finding the integral, then again, just you see all that here is force. I called it earlier weight, but I also highlight that in red ink, that was force, the amount of force to lift the remaining length after we have lifted away the x meters. Okay, and that with that continuously changing amount of force right here, we at every small instance where we reach infinitesimally small distance, force times distance. Okay, force times distance. That gives us the little amount of work, and that's why we're accumulating all of those little amount of work. Okay, it could be a lot at the starting, and it keep getting less work, but we have to accumulate all of that work amount to get our total work. But now what we have here is a successful setup for a definite integral. And so let's look at the good thing about this integral. That is a coefficient. We have our right to pull it all out in front of the integral. So now proceeding into the integral. So 2 times 9.8, and there's no need to calculate all that here as one number. So I'm going to leave that there as a product of two numbers. And then our integral becomes even simpler. An integral from 0, it's the integral from 0 to 28, and the function that depends on x that need to be integrated is 28 minus x times dx. Okay. All right, And so now at this point, before we proceed, I just need to make a remark for anyone. So it is also required that this video lesson is viewed after you have seen, after you understand what the fundamental theorem of calculus is. So in case you haven't been aware about what the fundamental theorem of calculus is, go ahead and pause the video here, find my other videos about what the fundamental theorem of calculus and what it does for us in solving an integral problem like this. Then once you understand what that is, the fundamental theorem of calculus, you can go ahead and resume this problem here. Okay, so now advancing with this problem here, I am going to look at the fundamental theorem of calculus. It tells us that to integrate this, I'm going to find the antiderivative. So the antiderivative here is 28x, and now I've left allow me to erase all of these extra notes here. Okay, so it's 28x minus a half x squared. But all of that here, don't forget, we still have the coefficient 2 times 9.8 in front of that. So, but it's just a coefficient. So coefficient stays together with your antiderivative. Okay, and then we're going to evaluate this antiderivative from 0 to 28. Okay, and so that's the result that came out from the fundamental theorem of calculus. So now I am going to quickly step away back to my computer station there to grab an answer for this. Okay, and you can see that it's easily just 9.8 with times 28 multiplied with 28 and minus 1/2. And I'm actually running out of space here, so allow me to write that in a different space. So how about right here? 2 times 9.8 times 28 times 28, okay, minus 1/2 with 28 square, okay. But then, so that's the antiderivative substituted at x equals 28. And I'm going to subtract, but look at the other one right here. It's going to be just 0 substituted in, so it's all just a 0 out. Okay, so now I'm going to go ahead and find the final answer for this. And then I'm going to write the final answer. So after this, correct, I'm going to write the final answer down here in this empty space right here. I apologize for such a small, narrow board space like that. All right, so my final answer came out. And so now, as I mentioned earlier, in this problem, we're working in SI units right here. So the SI units for the final SI units for total work here is going to be in joules. Okay, force in SI units is measured in Newton. So all of this here, the amount of force, that's all of that here. Weight or force, that's Newtons in SI units. And then now, after we found work in SI units is joules. So 7,683.2 joules. All right. That is our final answer, 7,683.2 joules. All right, so that's the whole idea about this problem right here. So I still want to, this problem is like that part where I was introducing in the general discussion lecture in a way that instead of doing it all at once, it could be too heavy. So I talked about the kind of problem where we have a man. I discussed about this in the general discussion lecture, but think about we have a man right here, right? And the man is pushing a heavy object right here, and as we going, right? That could be another person secretly keep adding more weight. So the idea is there. We still having changing amount of force as we go along the path, as we move the object, as we're exerting force to move the object in the distance right here. And so the lifting cable problem is here, but instead of the cable getting heavier, okay, the cable here is getting lighter. Unlike the kind of situation I described in the problem where the man was pushing that box, but it keeps getting heavier and heavier box. So here we have lighter and lighter chain that remains. Okay, but the idea now is that it's continuously changing amount of force that we have to exert on the object so that we can pull it from the beginning to the end of the path. Yeah. Okay, so now before I head into part B of this example, let me point out with this. So what if we really go with that? What if we went with that route where we try to, ask Superman, okay, to lift that for us? I know I can't do that, right, because it's quite heavy for me. But what if we ask a super strong man to lift the whole cable, pick the whole cable and lift it up? Okay, pick the whole cable and lift it up for us. Okay. What if we're asking somebody to pick it up? So think about from that. Maybe think about the situation where the height of the building is at least 28 or taller than 28, but from where the cable is 28 meters away from the top of the roof here, okay, and the cable is hung here as a coil, and if we try to lift all that, so the cable, even though being rolled into a roller here, but in the end it's 2 times 28, being a quite massive cable over here. That would be 56 kilograms. Okay, 56 kilograms. And we are going against gravity. So we're going to need to take that mass, like there's 56 kilograms, and everything is in SI units. We're multiplying with 9.8. So this is the amount of force that required for us to lift this. Okay, so that is we're going to need 548.8, okay, newtons to lift that. But then how far do we lift? 28 meters. It's not a joke, 28 meters. So now I am going to, so if we're doing it in that naive way, by asking anyone if anyone can possibly do that, take the whole roll, right, from 28 meters away, below that the building's roof like that, lift that up as a whole package. Instead of lifting it one by one, we take the whole roll, lift it up. Okay, then in that way, work is going to be, the amount of work we have to spend there is going to be whatever comes out from 548.8 newtons, and we're multiplying that with 28. And now I'm just trying to convince whoever viewing this lesson and learning from this lesson to see how important calculus is. That, and it helps us. I just want to point out that doing the two different math problems, it helps us to understand clearly that sometimes in our lives here, there are situations that we can be in control of, making lives easier for us. Look at how much force, how much work we have to spend for this. 28 meters away, I'm multiplying with 548.8, okay? I need to spend, according to my calculator, 15,366.4 joules, ladies and gentlemen, if we're doing that all at once. Okay? Instead of lifting it gradually up, okay, piece by piece, which gave us only 7,683.2 joules right here. And now if we ask anyone, even we asking Superman to lift that up for us, he's going to have to spend that much work, that much energy to lift that heavy cable, okay, 28 meters up against gravity. Okay, that is not a joke at all. It's almost like, it's literally double the amount of time, the amount of the efforts like that. If we're doing it that way, just take the whole package and lift it up. Okay, so I brought it up to point out that, that's the reason, we are not lifting it up all in one step. Okay, because a lot of time when I first brought this problem to students of mine in my class, and they asked, why not just take the whole cable and lift it up? That is the way. It seems simple for the math. It looks simple for the math, but when we're actually doing it, it's not that simple in life. And so when we're going with the way that's simpler for us to do it in life, then we have to do a little more complicated math problem. more calculus involved, so that we get the precise amount. We can figure out the precise amount of work that we spend for that. Okay. All right, and so now once you have seen enough generality of this kind of cable lifting or chain lifting problem or rope lifting problem right here, then now allow me to bring you into part B of our example, where it is technically another problem but a little more advanced version. I mean, a slightly more complicated situation. So let's now look at the wording description right here on the computer screen. So how much work is done lifting a 10-pound object, okay, a 10-pound object from the ground to the top of a 45-foot building, okay, from the ground to the top, okay, ground to the top of a 45-foot building, if the cable that's used here weighs 1.5 pounds per foot. Okay, and so before I proceed, I want to clarify the fact that this problem here, all of the weight and all of the weights, force, and work are all being measured in the American standard right here, which is, so 10 pounds right here is already the weight. It's not simply just the mass, it's the weight, okay, and being measured in the American standard. And then see, there's feet and foot right here instead of meters. So we're just not using the SI units here. We're using the specific American standard here for all of our measurements in this particular problem. And so the cable here weighs 1.5 pounds per foot. So this is also a density, but it's not that mass density. This is weight density. Okay. But now with all of this information, let me get back on the board and draw the picture, and we're going to derive the situation. So the object here is 10 pounds, right? And then the cable itself is the object is from the bottom, from the ground, from the bottom of the building to the top. We're trying to lift that object, and so it makes sense that we use the cable to be with the length 45 foot. So that's a one tricky part as well, even though it's not specifically mentioned. But the building is 45 feet tall, okay, or a 45 foot building, and then we want to lift the object from the ground to the top. That's why it makes sense that we have to use the cable at least from where we stand on top of the building, and the cable part that we're lifting has to be 45 feet long. Okay, and so now I'm going to get back to my board right here. And so I want you to take however I'm approaching this problem, to take this problem as closely as the one I have done in part A earlier, so that the closer you think and the more we think of that generality about cable lifting problem, then it will become a lot easier for us. The ground is here. Couldn't draw it too straight. Okay, so the ground, there's a building, 45 feet tall. Okay, that's going to be the distance that we need to lift the object right there. So the object is here, a very heavy object. Okay, that's the object. So yes, maybe we lose a little bit of length due to the size of the object, but that little amount right there should be neglectable. So in the end, we're still talking about moving it 45 feet distance. Okay, 45 feet distance from the ground to the top of the building. And so now, here's the cable. So the cable has its own weight, and this object here has its own weight. The weight of the object is constant. And the cable, the amount of cable, the cable itself, if we always look at the whole cable, then it's constant, yes. But the idea now, again, we're trying to do that. We're trying to lift it up one by one, step by step, gradually, from the top to the bottom. Because as I have pointed out earlier, now if we're asking Superman to do this kind of problem, take the whole cable, pack together with the object, and lift it up 45 feet to the top of the 45 feet building right there. That's going to be a lot of effort even for Superman. Okay, so in that way, now I'm going to define my x variable. The plan now, again, we're going to just lift it one by one, step by step, bit by bit. So x here is the amount, okay, the amount of cable. already lifted. Okay. So it's the length of the cable. I'm not talking about the weight. I'm talking about the length of the cable already lifted. Then at any point along our work right here, as we have lifted or as we have already lifted X amount of cable, then just like that fundamental I pointed out in part A earlier, it is going to be 45 foot, because like I explained earlier, we want to pull that object all the way from the bottom, from the ground, all the way to the top of the building and put it here. Okay, so that means we have to, the total distance here is 28, so the cable itself had to be at least 45 feet in length like that. Okay, so for the cable, and of course maybe we lose a little bit of length here due to the size of the object, but that should be neglectable. Okay, so in the end we can assume the easier case that it's just 45, and we're subtracting X. So this is the remaining length. So this is, I'll make a quick note right here, and then now since we already had some background in part A, I'm going to just make a quick note and I'm going to erase. So this is remaining length. Okay, remaining length of a cable to be lifted. Okay, and it also makes sense that once we lift some X distance away, then the object is kind of like hanging somewhere here, and we're lifting that up. That's the idea, okay? But so we heading up that way. So that's the remaining length to be lifted. That's what matters right there, okay? To be lifted. And then these are all in feet. So it's 45 minus X feet. In feet, okay? And so now, again, with that length right here, here's the part of making it a little crucial. So just the cable, then with this remaining length, 45 minus X, I am going to multiply with the 1.5. This is weight density. That part here, it's weight density 1.5 pounds per foot. So in every foot, it's 1.5 pounds heavy, okay? But now, so I have to get clear a little bit about the American convention. Now, in the American convention, once it's indicated in pounds, I mean it's already included gravitational acceleration in there already. So this is truly the weight right here. It's just somehow it's measured in the American convention. So that 1.5 already has the weight, the acceleration, the gravitational acceleration included in that, already including mass in there. Okay, so the American convention a lot of time don't go too precisely with the actual mass, but it goes by just the total weight after multiplying. So this is already mass multiplying with gravitational acceleration. That's what it is. So weight, and then we measure that in pounds for under the American convention. Okay, it's a little bit different with the SI's convention like that. Okay, so all we do, but now in the end it's weight per unit, or it's weight density, and so we just weight multiply with the remaining length, weight density multiplying with the remaining length. That gives us how much weight we need to lift, how much weight we need to lift for this remaining length up top of the building. Okay, but that's just for the cable. This is weight. I have to make note of that here. This is weight, okay, or total weight of cable, only the cable. That's the total weight to be lifted of the total cable. But life is not that simple in this problem, because why? We're not only lifting the cable. The cable itself is already heavy, but the cable is used to attach to the object 10 pounds heavy. Okay, and we're lifting that together. So that means the actual, so here, that's why I'm saying it's just the total weight of the cable. But the real total weight here is going to be plus 10. Whatever this in pounds, that's the total weight of the cable. This is weight of objects, okay? Weight of the object. That's what it is, okay? It's the weight of the object. Okay, and so now, but in the end, if we're totaling this up and trying to lift, the idea, again, still the same with that fundamental. As we keep lifting, as we have achieved more x distance, more length x being lifted already, then we have less amount of force left. We have less weight. The amount of weight total here is keep getting less and less and less, depending on how much we have already pulled for that cable right there. All right, and so now I'm gonna again navigate to my other board. 1.5 times 45 minus x, but I need to add 10. With that there, now I'm going to call this, allow me to quickly make a note right here. I'm going to call dx is going to be the vertical distance, okay? The vertical distance to lift 45 minus x length of cable. Okay, I could have also worded it this way back in part A of the example as well. But see, precisely speaking, whatever the length there, we're trying to lift infinitesimally small amount, okay, a vertical distance to lift this amount. Okay? And so now it's a different. So now with that understanding, I am going to multiply that with the dx with that. So at any instance, I have 45 minus x. I'm going to lift it up a little bit amount. Okay? And so that's going to be my little work amount right there. The little work amount, because now we have this, see, it's total weight, and this is force multiplied with the distance. Okay? And I wrote down the definition of distance earlier, and I had to erase to make space for myself right here. Force times distance. But that's just for little work, because, and remember, you got to keep in mind one thing, that this amount stays very instantaneously. That's why, you know, when I was defining that dx was the vertical distance to lift this much, but see, to lift that much, it only lasts for an infinitesimally small amount, because if it's a long distance right there to lift, if it's a big dx, then it's going to be significantly changed so much in that. Okay, and so it's no longer, it's 45 minus x. It's just a general expression, but it keeps getting less and less and less value as x changing, and that's the idea right there. Okay, and so now in that way, generally as an expression, it's 1.5 times 45 minus x was plus 10. Okay, that's the total force, the total weight, and we're gonna try to lift it up in the dx distance right here. That's the little amount of work. So now total work is just like that fundamental we have done in part A. Total work, and this concept right here, this fundamental comes out from the general lecture over here, is accumulation from some start to the end of our work right here of all the little w, of all the dw's right there, of all the little work amounts. And so now accumulating all of those, let's see what happens. Okay, so all of the dw is here. So I'm looking at 1.5 in parentheses 45 minus x plus 10, okay, with the dx. And that's the accumulation of all the little work amounts. And then we're accumulating from starts to an end right there. That's how we're doing it. Okay, and so now, again, I am going to swing back to my other board to point out how we recognize the start and the end of this accumulation. And so just like how I was saying that earlier, right when we, at that instance, when we get into this particular part B of the problem, right, think as closely as we can to part A that we did. So the idea now is that when we start, we have 0 feet at start. And then when we finish with the work, we will pull 45 feet away completely. So in that way, right here, the start would be the start in my explanation here. And I had more detailed explanation in the earlier part of the example. X equals 0 to be at start. Okay. And then x equals 45 feet to be at the end. Okay, so in that way, now I'm ready for completing my integral setup right here. Start at 0, and the end here is at 45. Okay, the end is at 45 feet. Now, ladies and gentlemen, we have a complete integral setup. Okay, so now, but slightly unlike part A that I've done, this is not a common factor, so don't pull it out in front of the parentheses, in front of the integral yet. We have to carefully distribute this and combine like terms and all that. Okay, And so before getting the integral, it's 0 to 45, okay? And then I'm looking at 67.5 minus 1.5x plus 15. Okay, dx, and of course these two terms here are constant term. We can combine them, but they are not, once again, they are not coefficients to be placed in front of the integral. Okay? And so now in the next step, I'm looking at the integral from 0 to 45. Okay, and it's with dx. Here I'm looking at 1.5x plus 82.5. All right. And so now, with this problem here, we can go ahead and use the fundamental theorem of calculus to get it done. And of course, I mentioned about the fundamental theorem of calculus earlier when we were working with part A earlier. And so now in that same experience, now fundamental theorem of calculus tells me that I can do 1.5 x squared over 2. This is the antiderivative of 1.5x plus 82.5x. This is the antiderivative of 82.5. This is the total antiderivative of the entire function. And we're now going to evaluate this antiderivative from 0 to 45. Okay, and so now that means we're looking at 1.5 over 2 times 45 squared plus 82.5 times 45. Okay, and then all of that there is the antiderivative here substituted, evaluated at x equals 45. And then I'm going to subtract out the same antiderivative evaluated at 0. At the 0. With that 0 here, one substituted in, it's just simply a 0 out right there. Okay, it's just a 0 out. And so now after this setting up right here, after this setup, I am going to quickly swing over to my computer station and get the final calculated answer for this. Okay. All right, so I now have the final answer here. So the final answer here was calculated to be 1,968.75. But be careful, as I've been mentioning quite a few times, in this part B of the example, we are working with the American standard. So for the American standard, when it comes to the work, this is foot-pounds. Okay, this is foot-pounds, not joules. Okay, so joule is the SI units, but here, since everything is measured in the American convention, in the American standard, and this is foot-pounds right here. That's the total final amount of work right here. Okay, 1,968.75 foot-pounds right there. And that comes after successfully integrating, taking the integral, the definite integral of that definite integral right here, and then the work is all done here. Okay.